Okay, now we are getting onto the curve sketching topic. So, as you might have been able to kind of tell, we're already kind of going into a little bit, but now we're going to get into some of the other things that you need to know for finding the features of a function, the things that you're going to need to label if you're asked to sketch a curve. So, other than points of inflection, the other thing that you're most likely going to be asked to label is going to be the stationary points. Remember, the stationary points occur when the second derivative, or sorry, when the first derivative is equal to 0. So, obviously, you've probably gone over finding stationary points before. We're going to go over an example in a second. But once you've found the point when the first derivative equals 0, you need to determine the nature of the stationary point. And that means like whether it is a maximum point or a minimum point. So we have two methods for finding the nature of a stationary point. The first one is using a table of values. So this is similar to what we've been doing in the previous examples where we've been using tables of value. What you're going to be doing here is you're going to pick a x value on either side of your point where the first derivative equals 0. So here we're going to say that it's occurring at 2. And then you're going to check the value, whether it's a positive or negative, of the derivative on either side. And this is going to tell you the nature of the stationary point. So if in our example here, the first derivative is positive on this side and negative on this side, this tells us that our curve is going to look like this, because it's going to be increasing, then it's going to have our stationary point, and then it's going to be decreasing. So it tells us that our curve has a local maximum point. Now, if we switched this around, if you had kind of the opposite scenario, if we had negative and then positive, it tells us our curve is going to be decreasing, then it's going to reach 0, then it's going to be increasing. So it is a local minimum point. So that is how we can use a table of values. And what we often call this is like the first derivative test. The second option is to use what we call the second derivative test, which is where we substitute the x value that we found into the second derivative. And the reason that this works is because remember our second derivative tells us about the concavity of the curve. So if our curve, I'll draw this for you guys, if our curve is a local minimum, then it's going to be concave up, which means that our second derivative is going to be greater than 0. And if our curve is a local maximum, then it's going to be concave down, which means that our second derivative is going to be less than 0. So this is why subbing into our second derivative helps. Like it really tells us about the concavity, but then the concavity tells us about the nature of the stationary point. So you can either remember these two rules down here, the ones here. You can remember them just kind of by remembering this process, or the way that I remember them probably isn't actually that helpful, but I just couldn't think of any other way, is that it's just kind of like the opposite of what you'd expect. You know what I mean? Like, if the second derivative is positive, then it's a local minimum. So it's kind of like the opposite, and the same thing here. If the second derivative is negative, then it's a local maximum. And this can kind of get confusing because for all of the other rules, they kind of make sense. If it's second derivative is greater than 0, then it's concave up. If the first derivative is greater than 0, then the curve is positive. All this kind of stuff, but I just kind of remember that, like, for determining the nature of a stationary point, using the second derivative test, it's the opposite. Again, that probably isn't the best way to remember it. I just couldn't really think of anything more creative. But If you guys can think of anything more creative or if you've learned anything more creative, please feel free to tell me. I still have to remember this rule to this day, and I still sometimes get it confused. Okay, so now we are going to get onto an example of curve sketching. So in this example here, we need to find the first derivative, the second derivative. We then need to find any stationary points and determine the nature of those stationary points. And then we need to determine any inflection points. So this is kind of like a culmination of all the content that we've been doing so far in the lecture. So let's get into it. So firstly, we need to find the first derivative and second derivative. So our first derivative is going to be equal to 3x squared, take 3. Our second derivative is going to be equal to 6x. Remember, we're finding the derivative of the first derivative. And now we need to determine any stationary points and their nature. So remember, a stationary point occurs when the first derivative is equal to 0. So we're going to find when the first derivative is equal to 0. So we're going to let 0 equal 3x squared, take 3. The only unknown here that we have is x squared, so we can just solve this algebraically. We are going to have 3 equals 3x squared. X squared is going to be squared. That was the ugliest 2 I've ever seen in my life. My deepest apologies. All of my private tutoring students know just how hectic my numbers can get sometimes. So we're going to have that x squared equals 1. And remember, when you are solving an equation where you're using the square root, you always need to remember the plus or minus of square root 1, because 1 squared is equal to 1 and negative 1 squared is equal to 1. So always remember that when you're solving like quadratic equations. Okay, so this tells us when the stationary points occur, but now we need to determine the nature of the stationary points. So I'm going to use the second derivative test just because we've been doing table of values, not specifically for this purpose, but table of values throughout the rest of the lecture. So we're going to sub these two x values into our second derivative, and this is going to tell us about the nature of the stationary points. So f double dash for 1 and f double dash for negative 1. So for 1, it's going to be positive, and for negative 1, it's going to be negative, because we just have 6 times 1 and 6 times negative 1. Now remember, if our second derivative is positive, it's concave up, which means it is a local minimum stationary point. If our second derivative is negative, which means we have a concave down curve, which means that the nature of our stationary point is a local maximum. So this tells us the nature of the stationary points and their coordinates. One more thing that we need to find is the y value of these two stationary points, just because it will help us graph and will also give the necessary information asked for in a question. Usually when you're asked a question for curve sketching, they'll ask you to draw the curve out and label any of the interesting points. Interesting points being like intercepts, stationary points, inflection points, all that kind of stuff. And you need to include both components of the coordinate, being the x and y values. So the function of 1 is going to give us 1 cubed, take 3, which is going to give us negative 2. Sorry, I wrote that the wrong way. Of 1 is going to give us a value of negative 2. and then the function of -1 is going to give us -1 cubed, which is -1 plus 3, which is going to give us +2. So our 2 points of inflection are going to be 1, -2, and -1, 2. Now we need to determine any inflection points. So remember, the inflection points occur when the second derivative is equal to 0. And that is our first requirement. So obviously our second derivative is going to be equal to 0 when x equals 0. And now we need to fulfill the second requirement, which is that the concavity around this point changes. So again, we're going to do a table of values. So we're going to have x, we're going to have our second derivative. Our point is going to be 0, and at this point our second derivative is going to be equal to 0. Now we're just going to pick two values on either side, pick one, and we're going to determine the value of the second derivative. So remember, our second derivative of x is 6x. So 6 times -1 is negative, 6 times +1 is positive. So this tells us that the concavity around our point of inflection changes, which means it is in fact a point of inflection, which is brilliant. So now we're going to get onto the last step, which is that we're going to graph it. I apologize if this is a little bit messy. So we're going to have y and x. So our point of inflection is going to occur at 0. We're going to actually need to firstly determine, or we're going to plot down the stationary points. So remember, at 1, -2. So we're going to have 1 down here, 1, -2, and then at -1, 2 are going to be our two stationary points. Now we know that our point of inflection is going to occur at 0, and we know that the nature of our stationary points is going to be a maximum here and a minimum here, and that's what we found in the last slide. So at 1, we're going to have a minimum, and at -1, we're going to have a maximum. So kind of drawing the rest of this out. This is what we get. And I apologize for the messiness. And this kind of corroborates that we have our point of inflection here at 0. So yeah, this is how we can use the stationary points and the points of inflection to graph a curve. Telling us information about the nature of the stationary points and about the concavity of the curve. The one more thing that you need to do is probably find the intercepts, which you should know how to do. But other than that, that is basically the basics of curve sketching for polynomials. So we're going to go over another example again, and this one is a little bit more difficult, but it also kind of illustrates a key point, or like a key tip that I'd recommend you guys remember for any kind of question involving calculus. And we'll get into that. So firstly, we need to find the first derivative, and then we need to determine any stationary points and use a table of values to determine their nature. So what we have here for our function is we have a product, because we have x multiplied by kind of a different function, which is x take 2 cubed. So we have a product. The other thing that we have is a function to a power. So we have x take 2, which is kind of like a linear function within itself, to a power. So whenever we have a function to a power, we need to use the chain rule. So in this question here, to find the derivative, we are going to have to use the product rule and the chain rule. One more tip that I have before we actually get into deriving it is kind of when you're reading through a question, if you see like that the first part like asks you to prove something or show something, and then kind of use that result in the next part of the question like we do here, it usually means that like this first part here is like a little bit difficult. And if you can't figure this out on the day of an exam, you attempt this first part, but you just can't figure out how to show that the first derivative is equal to this, it means you just need to take this result and roll over to the next question and kind of stop wasting time on this first part. The reason that people who write exams do this is because like they don't want you to lose too many marks just because you can't find the answer to the first part of the question if that first part of the question is necessary to subsequent parts. So, takeaway, if you get this kind of question where you have like something you need to prove in the first part and then use that in the second part, if you can't prove the first part, just leave it to the end of the exam and just kind of take this result and use it, and hopefully you'll get marks for the second part of the question as well. Okay, but now we're going to get into actually deriving this. So, as I said, we're going to have to use the product rule. So we're going to have U equals X and V equals X take 2 cubed. Our U dash is going to be 1. Our V dash, remember, we're going to use our chain rule here, so we're going to take this 3 out the front, leave what's in the brackets, take this old power by 1, we're going to reduce this old power, giving us 2. Now we're going to multiply by the derivative, the thing we just left by itself, the thing we just covered over, the thing we just ignored. The derivative of X take 2, the thing we just ignored, is just going to be 1. So using our product rule, we are going to have uv dash plus u dash v, which is going to give us 3x x take 2 squared plus x take 2 cubed. Now, one more thing that I'd recommend to you guys is when you're going through your exam, if you're using kind of like a simple rule, such as the product rule, make sure you either write down a formula or just write down that you use the product rule if you don't need to write down the formula. Because otherwise, if you have a look at the marking guides, especially for the QCEE externals, maybe not for your internal exams written by your teacher, but definitely for the external exams, they always allocate a mark to kind of specifying what differentiation rule you're using. So either write down the formula or write down, just say like write like product rule in words. And then you'll get the marks for that. Okay. Now we need to prove that this is equal to what we have over here. So what we have over here is kind of a factored version of this. So a tip for when you are doing like a proof question, if you need to like show a result, usually you just kind of need to like look at what you need to prove and then look at what you have currently and kind of match the elements. So the similar elements that I can see here is that here we have an x take 2 squared, which is factorized out. So I'm going to factorize out the x take 2 squared firstly. So we can factorize out x take 2 squared. And this is going to leave us in big brackets with 3x plus x take 2, because that's what we've been left over with. The other thing that I notice about what we've been asked to prove is that we have a 2 out the front and that we don't have an x out the front like we did here. So we don't want to bring an x out, but we do want to bring a 2 out. And we do also want to have a component that looks like 2x take 1. And this is kind of what we need to do in the remaining. So, this section here, we want to match up to this section here because we've already got the x take 2 squared down pat. So what I'm going to do here is just expand what we have and see where that gets us. So we're going to have 3x plus x, which is going to give us 4x take 2. So what I recognize here is that for this second part here, we can factorize out 2 and then be left with 2x take 1 because 2x take 1 is equal to 4x take 2. So we can factorize out that 2, which gives us exactly what we want. So we're going to be left with 2 outside of 2x take 1, x take 2 squared. So that is our proven result. Now, the tip that is kind of inherent to this question that I was talking about, which is really important, we are going to get to now. And this is kind of the purpose of this first step here. So now we need to find any stationary points and then use a table of values to determine the nature. So we're going to have our derivative being outside of 2x plus 1, and then we're going to have x take 2 squared. It's going to be take 1, sorry. So now we need to find any stationary points, and we need to find when this first derivative is equal to 0. So we're going to let 0 equals 2x take 1, x take 2 squared. Now, really quickly, just take 1 second to think about how we could solve this, how we could find when x is equal to 0. So, hopefully you had the chance to think about that. What we can do is we can use the null factor theorem, similarly to if we're kind of factorizing a quadratic and then finding the solutions for it. So we can use the null factor theorem. We can say that 0 is going to be equal to 2x take 1, and 0 is going to be equal to x take 2 squared. And then we can solve it from there. So this is going to give us that x is equal to 1/2, and then x is equal to 2. And that was really simple. What I want to point out to you guys is that if we had tried to do a similar thing, just by using the first derivative that we found to begin with, which was this one here, 3x, x take 2 squared plus x take 2 cubed, it would have been impossible because we wouldn't have been able to use the null factor theorem, right? So the tip that I have for you guys is if you're doing anything with calculus and you need to find like a stationary point, or you need to find a point of inflection, or like even more generally, if you have an equation and you need to find when it's equal to 0, factorize it. Factorize it. Like I've done so many questions in all of year 12, like practicing all these kinds of questions in methods. At the level you guys are at, if you get a really complicated equation and it's equal to 0, the only reason or the only thing they're ever going to be able to expect you to do to solve that complicated equation is to factorize and use a null factor theorem. So this is kind of like a similar thing that we do when we are solving quadratics, which maybe you guys actually haven't thought about before. It was kind of like a realization that I had when I first started using this tip that I'm talking about, is if you have like a quadratic, x squared plus x plus 1, whatever quadratic. What we've kind of learned in like year 10 and year 11 is just like, oh, we just like factorize it and then use the null factor theorem, right? And that's because like we can't solve the quadratic in its unfactored form. And that's exactly the same process that we've been going through just now. We had this derivative in its unfactored form, and then to solve it, we needed to factorize it and use the null factor theorem. So, as I said, it's kind of a widespread and very useful tip, even in like completely different areas of maths. Anything that you're going to be doing later in the year, even when you're getting into statistics and stuff like that and methods, it'll still be useful to remember that. If you want an equation equal to 0, factorize, use the null factor theorem. Okay, moving on. Now I need to determine the nature of these stationary points. So we need to use a table of values as the question specified. So we're going to have x, and we're going to have our first derivative. So we're going to have x equals a half, x equals 2, then we're just going to pick values in between these. So we're going to have 0, 1, 3. We know that at a half and 2, our first derivative is going to be equal to 0. Now I need to determine the value of the derivative at these other values, 0, 1, and 3. So, really quickly going to figure those out. Okay, so what these look like is that this one here is negative, this one here is positive, and this one here is positive. So I just did that using the table function on my graphics calculator or using Desmos. Obviously, if you're in an exam, you'll need to use a table function on your calculator. If it's a tech-free exam, then they'll probably give you something easier to work with. Excuse me. So now we need to determine the nature of the stationary point. So I'm just really quickly going to like graph out what this looks like underneath here. So we're going to have a function that has a negative gradient here. Then it's going to reach 0. Then it's going to be positive. Then it's get more and more flat. And then it's going to be positive again. So this is what our function looks like, right? We kind of have a stationary point here and a stationary point here. So, as a quick exercise, have a think about where the point of inflection would be here, or how many points of inflection there would be. Take a quick second to pause the recording to think about this. But there is actually only one point of inflection, which is right here, because this is where the concavity changes. This section here is not a point of inflection. Oh, sorry, it is a point of inflection. My mistake. This one is also a point of inflection because the concavity around that point also changes, because here it is concave down, and then here it is concave up. My mistake. So we do have 2 points of inflection here, and then at this point here we have a stationary point and a point of inflection. Okay. So the nature of our stationary points, this is going to be a local minimum. And then this here, because it is a stationary point and a point of inflection, is going to be what we call a horizontal point of inflection. So those are the nature of our two stationary points. Okay, now we have one more harder example. So we have a curve y equals ax squared plus bx plus c, passing through the point 1, 4 and negative 1, 6, and it obtains its maximum value when x equals negative a half, and we need to find a, b, and c. So, quick tip for you guys. If you want to have a think about this question before we go to the solution, again, pause the recording. But quick tip for you guys is if you are asked to find multiple values, like the coefficients of the variables in a curve, so as we have been here, A, B, and C, the coefficients, the derivative is really, really useful because as you kind of go down the derivative, the numbers are eliminated, right? So like when we find this first derivative here, we're going to eliminate C, which makes our equation simpler because now we don't have C and we do have values for the derivative. So it's really useful to kind of use the derivatives because it eliminates those values. So our first derivative is going to be 2ax plus b. Now, we're going to write down the information that we have been given and use that to find a, b, and c. So the information that we've been given is two coordinates and something about its derivative. So we know that a maximum point occurs when x is equal to negative 0.5. So we know that y dash equals 0 at x equals negative 0.5. And remember, this is a minimum. So we have one more condition, which is that the second derivative is going to be less than 0. So we also need to prove that for this information. So what I'm going to do first up is sub this information into our derivative function. So we're going to have 0 equals 2a times negative 0.5 plus b. So this is going to give us 0 equals negative a plus b, which gives us that a is equal to b. So this is really helpful information. We don't yet have a value, but what we do have is some more information that we can use using maybe some simultaneous equations. So what we also have is these two coordinates. We can sub in these x and y values to come up with two different equations in terms of a, b, and c. So subbing in 1, 4, we are going to get 4 equals a times 1 squared plus b times 1 plus c. And then subbing in negative 1, 6, we are going to get 6 equals a times negative 1 squared, which is just a. Take b, we have b times negative 1 plus c. So this is really useful. We now have 3 equations and 3 unknowns, which means we can use simultaneous equations to find a, b, and c. So we know that a and b are equal. We can sub these two in together to get 4 equals a. We're going to sub a equals b, which is going to give us a plus c. So 4 is equal to 2a plus c. Therefore, c is going to be equal to 4 minus 2a. We can sub equations 1 and 3 into this one over here. So we're going to get 6 equals a, take a plus 4, take 2a. So we're going to get 6 equals, so a take a is going to cancel. We're going to get negative 2a. We're going to take that 4 over to the other side, which is going to give us that a is equal to 1. Therefore, b is also going to be equal to 1, remember, because a equals b. And then we can sub this in here to find C. So we're going to get 4 take 2 times 1, which is just 2. So these are all of the values for A, B, and C. Again, I know this was a harder example. If you didn't quite catch everything, remember to look through the recording. But yeah, the basics of this one to remember is that just if you're asked to find the coefficient of the unknowns for a curve using derivatives, you're most likely going to be needing to derive and then kind of utilize the fact that as you derive down, the values drop off. And then you're most likely going to be using simultaneous equations to find the values. The other thing that I'd recommend for these types of questions, but also questions worded like this in general, any kind of worded question, is if you are given information that is maybe not in numbers. So, it's kind of easy once you're given a worded question to write down the numbers that you're given. But if you're given information that's not in numbers, like we were here, that it obtained its maximum value, convert the worded information into numbers. So the maximum value tells us that maximum value means stationary point, means that the first derivative equals 0. And once you've written all of that information down, even if initially upon reading the question you really had no idea where to go with it, once you're looking at all the numbers written down, it becomes a lot easier to make the connections in your mind. At least I find it a little bit easier. And I still use this strategy when I'm doing my economics degree in university. So it really does work. And yeah, I think that's everything for that question. Oh, one more thing that I should mention is I did mention that the condition for this was that the second derivative was less than 0. You can go ahead and prove that the second derivative is less than 0. But another thing that you could say is because this curve is a parabola, it's only going to have one stationary point. So that means that this point that we found, is the only stationary point. As a general rule, especially when you're getting into curve sketching, a curve can only have the number of stationary points that's one less than its highest power. So, because a quadratic, the highest power is 2, so it can only have a maximum of one stationary point. Similarly, for a cubic, because the highest power of a cubic is 3, it typically has a maximum of 2 stationary points. So a cubic can look like this, but a cubic can also look like this, and it only has one stationary point. So that's what I mean. It's cubic, the highest power is 3, it can have a maximum of 2 stationary points, but it can still have one. Okay. Yeah, that was just a general tip for curve sketching of polynomials.